Okay, so these lectures are going to be on superstring amplitudes. The superstring amplitudes, of course, is a very big subject, and so I had to decide on where to begin. And I was told that most of you probably would have seen some aspects of two-dimensional conformal field theories. Okay. So that will be more or less my starting point. I'll assume that you are familiar with at least some aspects of two-dimensional conformal field theories. Okay, but I'll not assume too much about this. Okay. So let me begin by a review of the bosonic string worldsheet. And this is usually developed in analogy with point particles. Okay. So propagation of a particle describes a world line. Is this visible, what I am writing? And so this is described by specifying a function, a set of functions where x mu are the space-time coordinates and tau is an intrinsic parameter that labels the world line. And the choice of tau in fact is completely arbitrary. Okay. So tau going to any function of tau is a symmetry. And this in fact is a gauge symmetry on the world line. So in the same spirit, okay, propagation of a string and throughout this lecture I will be considering mostly closed strings. Okay, but we could also analyze open strings using similar techniques. So propagation of a string describes a world sheet and this means that we have to specify x mu now as a function of two variables tau and sigma, because as a string moves it's a two-dimensional surface and you have to specify x mu at each point on the two-dimensional surface. Okay. And again reparametrization of tau sigma is gauge symmetry. Gives you gauge symmetry. So when we gauge fix, we get Fourier-Prof of ghosts. So at the end it turns out that together the x mu's and the ghosts give a two-dimensional CFT, and this will be our starting point. Okay, so what I am going to do is to now write down the various features of this two-dimensional CFT that we get by quantizing a string and gauge fixing the reparametrization that is there on the worldsheet. Okay. I will not tell you how exactly that it's derived, okay, the precise form of the worldsheet CFT, but that's standard gauge fixing procedure of a gauge symmetry. Okay. So let me begin by writing down the field content of the theory. So fields are matter CFT with central charge 26 and these are in fact come from the X mu's. Okay. So each X mu is a scalar field, a free scalar field in 2 dimensions. Okay. So each X mu contributes 1 to the central charge, okay, and the total central charge is 26 because mu runs over 26 values. Okay, why 26 we will see soon. Then the ghost there are 4 sets of ghost fields. B, we call them BC, B bar and C bar. These two are holomorphic, okay, which basically means that their equations of motion is simply that the anti-holomorphic derivative of B and C are 0 and these are anti-holomorphic. Okay, so their equations of motion force them to be independent of Z and depend only on Z bar, okay, where Z and Z bar are the worldsheet complex coordinates. So the basic ingredient of describing this conformal field theory are the operator proton expansions. Or the OPs. Okay, so let me give the operator expansions and our convention will be that partial will mean derivative with respect to Z and partial bar will mean derivative with respect to Z bar. Okay, so these are Z, Z bar are the worldsheet complex coordinates. So the basic OPs that we'll need are these. Plus non-singular means NS means non-singular. And the final ingredient that we will need for the analysis are the expressions for the energy momentum tensor. Okay, and from there we can derive more or less everything else. And similarly Tx bar and Tbc bar. Okay, basically we replace the holomorphic fields by anti-holomorphic fields. Okay. So as I said, I have not given a derivation of these results. Okay, this is what comes if we start from the worldsheet theory of the X mu's and then gauge fix. Okay, and eventually we arrive at a conformal field theory which has these properties. Okay, so this will be our starting point in the analysis. But are there any questions on this? Is it clear what this means? It's okay. Is there some clarification needed? Okay, so we'll now see how to make use of these. Okay, so we'll do some simple calculations and that will illustrate why these are useful. So let's use this to calculate some operator expansion Tx of z with del x mu of w. So Tx is given by this, okay, product of two del x. So we have to look at the singular part of the OP of the del x's that are coming from here with del x mu itself. Okay, and for this we use this result over here. Okay. So there are two of these. So you can get a non-singular, a singular part of OP either by taking the operator expansion of this with this, or the operator expansion of this with this. Okay, both give the same result, but gives a factor of 2. Okay. So the net result is that the leading singular part of this is given by 1 over z minus w square del x mu of w, plus there are higher order terms, okay, which I am not writing down. Okay. So what happens here is that there is a, in the OP of x del x with del x there is a minus half, right? So that 1 over 2 got cancelled because there are two terms, one where you get the OP of this with this and another where you get the OP of this with this, and the minus sign got cancelled because there is a minus sign in the expression for Tx. So this tells us that this has conformal weight. Okay, here I have to use a notation. I will call this 0, 1. Okay. So these two, okay, basically label the anti-holomorphic and holomorphic conformal weights. So general H bar H is the conformal weight of a field with weight h bar and holomorphic weight h. Okay, that will be the convention that I'll be using. Okay. So here, because this is coming from the OPU with Tx, okay, it's a holomorphic conformal weight. That's why we are getting a factor 1 here. Okay. If we calculate the OPU with T bar with del x mu, then it's non-singular OP, right? So that's what shows that it has no anti-holomorphic conformal weight. Okay, that's why it's 0. Is this notation clear? Okay, so when I say conformal weight h bar h, right, the first one is the anti-holomorphic conformal weight, the second one is the holomorphic conformal weight. So let's do TBC of Z with B of W. So reading singular part, let's look at the TBC, right? Minus 2BC derivative of C. So a leading singular part will come from the C with B. Maybe I should have also said here, I should have said these are Grassmann odd objects. Okay. So this OP, for example, also means that C of W, B of Z is minus 1 over Z minus W. Okay, this minus because we have exchanged the position of C and B, which I can also write as 1 over W minus Z. Okay. So with this, let's do this calculation. So this is TBC is minus 2B del C plus C del B. This is at Z and B of W. And we can see that the leading singular piece will come from the OP of derivative of C with B, because we are taking a derivative. So 1 over Z minus W will become 1 over Z minus W square, and there will be an extra minus sign. So this gives you 2 over Z minus W square B of W plus lower order terms. Similarly, TBC of Z with C of W gives you minus 1 over Z minus W square C of W plus rest. So this means that B has weight 0, 2 and C has weight 0, minus 1. Is this clear? Right? If it's not clear, you can just do this exercise easily. Okay, at home, just use the basic OPs that I have written, okay, and then simply try to carefully keep track of where the singular pieces are coming from. Okay, and if you do that carefully, okay, then you will not only be able to reproduce the most singular term, but there is also 1 over Z minus W term, and that also you should be able to reproduce by looking at the operator expansion. Yes, yes, indeed. So dots also include singular terms. So these also have 1 over Z minus W terms. Okay. And you can repeat this for the anti-holomorphic fields, okay, which is basically identical with Z replaced by Z bar and W replaced by W bar. So I'm not writing it here.
In that OP on the right side of the right,
Yes.
both B and C are defined at the same point B, right?
Both B and C, which here? Yeah, yeah, yeah.
Like on the second line.
Yeah, these are also at the same point, exactly.
At the same point. So when you take the derivative, the orthogonal derivative,
Yes.
then if you take it with respect to C, then it should also act on B, right?
Okay. So this, what this means, maybe I should have said this, that this is whenever you are defining a composite operator, you do normal ordering. Right. So you subtract off any singularity that B and del C might have. Right. So when I write B del C, for example, right, let me write it here. So B del C so this will mean that it's B of W del C of Z. This is a limit limit W goes to Z, B of W del C of Z minus 1 over W minus Z square. Okay. Because you see B of W C of Z has 1 over W minus Z. Right. So when you take the derivative, it's 1 over W minus Z square. Right. So that you subtract out. Right. This is what is called a conformal norm ordering. After that, any OP that you have to calculate is with between this and this. Okay. So when you calculate del C with B, okay, it will give you a derivative of 1 over Z minus W, right, which produces minus 1 over Z minus W square. Right. That's what is responsible for this term. Is that okay? Any other question? That's a big backpack. Okay, any other question on this? Okay, so now we want to do the OP of energy momentum tensor with itself. Tx of Z with Tx of W. So T is here. So when you calculate the OP of this with itself, you see there are this. So there are two possible contractions, right? One where this can contract to the first element of the second T, and the second one contracts to the first one, and vice versa. Okay. Each of them gives you a minus 1 over 2Z minus W square. Okay. So you square it, right? 1 over 4Z minus W square, and you multiply by 2 because there are two possibilities, right? There are two possible contractions. So each mu gives you a 1 over 2Z minus W square. Okay. So this will give you D over 2Z minus W to the 4. Sorry, not Z minus W square, because it's square of Z minus W square, so Z minus W to the 4. And then there are subleading terms, okay, which I have not written. Okay, these also have singular terms. Is this clear? A slightly more involved calculation is this one, dBc of Z, and D in this case is basically 26. I have already said D equal to 26, right? But we will now see why. TBC of Z with TBC of W this is an exercise, is minus 13 over z minus w square w to the 4 plus lower order terms. When you combine these two, we see that if you define t as tx plus tbc, then t of z with t of w gives you d minus 26 over 2 times z minus w to the 4 plus lower order terms. And we see that this term vanishes 0 for d equal to 26. Okay, so the total central charge of the matter and the ghost system vanishes when d is equal to 26. This will have many other consequences, but this is the first time we see that d equal to 26 is somewhat special, that the total central charge of the matter and ghost system vanishes. We'll see. I'll not tell you now, but when you come to BRST charge, right, we'll see that this d minus 26 again comes in there. Right, because that's a really important part. Yes, otherwise these two theories are completely decoupled. Exactly. Eventually, okay, as a theory, they will be completely decoupled at the worldsheet level, but we will see that when you actually look at the correlation functions, right, the correlation functions have to be calculated for this combined system. Okay, and there the operators that we'll be considering have matter and ghost entangled, right? They are not independent objects. Okay, so now some notations and definitions. So take a conformal transformation. Z goes to some function of Z. Okay. So we'll assume that f of Z is analytic in some domain, doesn't have to be the full complex plane. Okay, but if it's analytic only in a certain domain, we can use this conformal transformation only within that domain. Okay, but that will be good enough for us. And suppose phi is some local field or operator in the theory, some local field operator. Okay, phi I am not assuming is holomorphic, so it can depend both on holomorphic and anti-holomorphic coordinates. Okay. Our definition will be that if circle phi, this is by definition the conformal transform of phi under F. Okay, so let me give some examples. So if phi is a primary of weight h bar h, then f dot phi okay, because this is the way a primary field operator is supposed to transform. Okay, it just picks up a factors of f prime z to the power h, f bar prime z bar to the power h bar, and it's evaluated at the new points f z bar. Okay, I'm thinking of this as active transformation on the fields. Is this clear? Prime is derivative, yes. So f prime of z is del z f of z. Thank you. Yes, f bar prime is del z bar f z bar. Okay, and for del z bar of f bar of z bar, right? If if f is I z, right, then f bar of z bar is minus I z bar, right? That's what you have to take the derivative of. But this definition also works for non-primaries, right? It's not restricted to primaries, except that for non-primaries, the transformation is not so simple. So non-primaries, right? Let me just work out an example. Okay. Take f of del c of z. Okay, this is a derivative. C of z is a primary of dimension 0 minus 1. Okay. But the derivative of c is not a primary, right? And we will see why it's not a primary, because we will explicitly work out its transformation law, and we will see that it doesn't take this form. So this I can write this as derivative of f dot c del cz. Okay, because f is like an operator acting on CFT, right? The derivative just comes out of f. So this is now c is a primary of dimension minus 1, 0 minus 1. So I can apply this rule. Okay. So this gives you f prime of z inverse c of f of z. So this has two terms. One is minus f double prime of z by f prime of z square C of f of z plus another term where the derivative acts on C, okay, that brings out a factor of f prime of z and that cancels this. So, that just gives you derivative of f of z. Okay, where this means derivative with respect to its argument, right. So, by chain rule I have just pulled out the f prime of z and cancelled against this. Okay, so this is the derivative of with respect to the argument. So, that is what this is. Okay. So, you see that if this term had not been there, okay, then this would have transformed like a dimension 0 0 primary, right, because it's just changing the argument, but h and h bar are both 0. But the presence of this factor, okay, tells us that it's not transforming as a primary, right. There are some additional terms in the transformation law. Okay, but you can work out the transformation of any field, okay, using this kind of manipulation.
But it is important that we know at least who is the prime and constructed out of this operator. The operator is constructed out of the prime.
Yeah, basically because everything is considered out of B, C and derivative of x and its derivatives, right? And B, C and del x, they are primaries, right? So you just apply derivatives on those and you can find out for any operator what the corresponding transformation law is. Okay, so for e to the I k dot x, right? E to the I k dot x you can show is the primary by looking at the OP of with t or t, right? And then again you can start from there and take the derivatives. Any other question? So this transformation will be useful, right? This notation will be useful. Okay, and I'll now introduce some spatial transformations which will be also useful. Yes. Pardon? Sorry, I didn't get a question. Oh, how did you get this? Okay, so first term is clear. See, you can think of the f dot c is like, you can think of this as a abstract operator in C in the CFT, C of z UF inverse. Right? This is an abstract CFT operator. Right? It knows nothing about z, and you are having del z of this, right? Okay. So this I can write as del z of UF CZ UF inverse. Okay, think of this UF, the F as an conjugation by an abstract CFT operator, right? And then it becomes clear that derivatives with respect to coordinates you can just pull in and out of this. Is that okay? Any other question? Yes. Yes, that's right. So this is derivative with respect to argument, right? That's why we pulled out an f prime of z and that got cancelled against this. So whenever I write this, it's derivative with respect to argument. Okay. So next, I will be describing the state operator correspondence, which again is a familiar concept in CFT. Okay, but let me just review this quickly anyway. So states. So you define a vacuum as the state such that T of 0, well, maybe write it this way. So, this is basically saying that vacuum is a state, okay, which does not know about any part, which in which no space time point play any particular role, right. So, T of z should not be singular, T of z acting on a vacuum should not be singular at any particular space time point, because that will give that space time point a particular role. Okay, so T of z should be finite for all z, and similarly T bar of z bar. Okay, and this is enough to define the vacuum uniquely in the theory. Then that point is getting a spatial role by the vacuum, right? And the point of the vacuum shouldn't give any point in on the plane any spatial role, right? So T of z on the vacuum should be non-singular everywhere, right? That's the basic point. Okay, and it's customary to define ln's by this expansion of T, ln bar by expansion as of T. T bar. So T of z is defined as sum over n ln z to the minus n minus 2 T bar of z bar and this implies that ln acting on the vacuum should be 0 for n greater than or equal to minus 1, and similarly ln bar acting on the vacuum equal to 0 for n greater than or equal to minus 1. Okay, because if you take n equal to minus 1, then the coefficient of L minus 1 is Z inverse, right? And that, so if L minus 1 on the vacuum is non-zero, then you get a pole. Then you get a 1 over Z, and that and it diverges at Z equal to 0. Okay. And then for any local operator phi Z Z bar, define the state phi as phi of 0 acting on the vacuum. Right? This is the state operator correspondence, that for every local operator phi, you can define a state by applying that operator value at 0 on the vacuum. Right? But what is special about conformal field theory is that this is a one-to-one correspondence, that for every local operator you can define a state, but also for every state you can find a local operator, unique local operator which has this property. Okay. So for this reason, it is often we can use states and operators interchangeably, right? And that's what we will be using. So when I talk about that we want to define a Hilbert space state, right? I could equally well give a local operator, okay, and that will describe a Hilbert space state uniquely, because you can evaluate at 0 and apply it on the vacuum. Okay. Now BPZ conjugate. Define the map I of z as 1 over z. Okay, so it takes z to z equal to 0 to z equal to infinity, and then we define the BPZ conjugate, which is the bra phi, which is okay. So you first conjugate phi by this z goes to 1 over z, and then apply on the bra vacuum. Are there questions? Well, that I mean this definition makes it's a definition at this stage, right? But this is useful because essentially what it is doing is that it takes a state that is created at 0, right, to a state that is created at infinity, right? And I mean normally this the insight for all this comes from the exponential map where you take z equal to e to the w, right, where z equal to 0 is like w to minus infinity, and z equal to infinity is like w going to infinity, right. So it's exchanging the in state and out state, right. That's what it takes the in state and maps it back to the out state.
So this conjugation can be interpreted as conjugation with respect to the inverse.
With the inverse symmetry, yes, yeah. So you follow exactly the same definition of f dot z phi that I gave, right, but you use this map. Pardon? That okay, this is the definition of the adjoint of phi, right. I mean that's the way we define it, okay? But this is not going to lead to a positive definite inner product, right. So we have the BPZ inner product, right, with phi L, say phi S with phi R is not going to be a positive definite inner product, but which is okay. I mean we don't really need positive definites at this stage. Yes. No, obvious, but you can prove that it's unique. Yeah, the Russell to infinite vacuum is unique. Yeah, basically you I mean look at the you assume that there are two SL to Z infinite vacuum, and then you show that the difference has basically zero correlation function with everything else. That's the way you define it. Because you can calculate the matrix element of the vacuum by from using these identities. Now, correlation functions in a CFT are defined. Suppose you have this is by definition the expectation value, the vacuum expectation value of the radial ordered product of operators where radial ordering means this is R stands for radial ordering. And this basically means that if mod Zi is larger than mod Zj, then phi I is to the left of phi j. Okay, so this is the analog of the time ordering. Okay, and it in fact does become the time ordering if we again use the exponential map. If we use z equal to e to the w, then radial ordering in z becomes ordering in real part of w, which you can think of as a time. Okay, but this is the way we for now we'll just take this as a definition of correlation function. And then we can state the property of the correlation function as a conformal invariance, which says that irrespective of what operators you have, this could be primaries, secondaries, doesn't matter. Product over I, phi I of zi bar is equal to product over I f dot phi I zi bar if okay. So this is what is called the SL to C transformation. We can put condition AD minus BC equal to 1, but it really doesn't matter. Otherwise, A, B, C, D are complex numbers. What is special about this map is that it takes a complex plane into itself in a one-to-one fashion. Complex plane plus the pointer infinity. It maps it to itself in a one-to-one fashion. Okay. And this you can show is a symmetry of the correlation function, okay, which basically is translated into this. That you take each phi I transformed by f, okay, following the procedure that I gave earlier, okay, and these two correlation functions are supposed to be the same. Is this clear? Are there questions? Okay. One way to prove this is to look at the infinitesimal version of this symmetry, right, where it becomes a commutator between L0 and L plus minus 1 with the rest of the operators, and then you use the fact that the of these properties, okay, and a similar property for the BPZ conjugate. Okay. Using that, we can show that this property holds. Any question on this? No, even then it's not true. If f is holomorphic in a region, right, but not holomorphic outside, then this is not true. It has to be really one-to-one map in the full complex plane.
It's holomorphic in the complex plane. It is not
Pardon?
if it's holomorphic function in the entire plane, it's not
Mobius, yeah, then this property doesn't hold. Then this property is not true. This statement is true only if it's a Mobius transformation. Yeah. Are there questions on what we discussed so far? Okay.
I have one question.
Yes.
So, about the uniqueness of vacuum here. So, can you prove it like this? You can take another PW on the left and bra 0, and then use the OP of PW to and those have only numbers on the numerators.
Yes.
And that should be 0, so that's why.
Well, basically, what suppose there is another 0 prime which has the same property, right? What you can show is that if you take the difference between 0 and 0 prime, right, that has basically 0 matrix elements of everything, all states, right? Which basically means that the difference between 0 and 0 prime is a state that you can set equal to 0, right? Because it has 0 matrix element of everything else. Right? That's one way to prove that the vacuum is unique. But it's specific to this class of theory that I'm describing here. Okay, there are other examples where if the vacuum itself is a somewhat ill-defined object, right? Like in Liouville theory, for example.
So for example, you comment that if the central charge is non-zero for the theory, then this relation may not be true.
If the central charge is non-zero, no, this relation is still true because this relation involves L0 and L plus minus 1, right? That is still true even if the central charge is non-zero. Okay, so let me begin by describing one consequence of this, the invariance under SL2C transformation. That in this correlation function, if mod Zi goes to infinity, right? Suppose you take one of the Zi's to be very large. Okay, so some particular, so for some particular I. And phi I is a primary of weight h bar h, then okay, so the behavior of this correlation function for large Zi is of the form Zi to the minus 2h, Zi bar to the power minus 2h bar. If you take Zi to be very large and if phi I is a primary of dimension hi bar. Hi, let me call it. Okay, hi bar, let me put I index here. And the way you can prove it is simply by applying this I. Okay, I is a SL2C transformation. To prove use Okay, in other words, if you apply I, right, what does it do? It takes Zi to 1 over Zi bar to 1 over Zi bar with some extra factors. Okay. Now, as Zi goes to infinity, the argument of that goes to 0. And then you simply use the fact that the correlation function must be regular at the origin because there is no other operators inside at the origin, right? And that produces this factor. Okay, this extra factor that you see here is essentially coming because when you apply I, right, there are some additional factors of Zi to the 2h that's responsible for those factors over there. The detailed proof I'll leave as an exercise. Here is the exercise. Now, based on all this, we will now discuss some peculiar properties of the BCCFT, okay, which is not what we normally see in the conformal field. Here is okay. So let's look at this. Let's introduce the definition of ghost number. So we define the ghost number of B as 0 minus 1, of C as 0 1, B bar as minus 1 0, and C bar as 1 0. Okay, so B carries ghost number 1, B carries ghost number minus 1, C carries ghost number 1, and you can define separate ghost numbers in the holomorphic and anti-holomorphic set. Now let's consider this correlation function B of Z, C of W. So this has some particular features, okay, which I will now list. So first of all, this as Z goes to W, it goes as 1 over Z minus W times the matrix element of the identity operator. This is identity, right, which you can also write as basically the inner product of vacuum with itself. This also has the property that it, as Z goes to infinity, it goes as Z to the minus 4. Okay, why? Because B has conformal 2. Okay. So as Z goes to infinity, by that identity that I showed here, by this relation over here, it will go as Z to the power minus 2 times 2, that's minus 4. And this also has the property that as W goes to infinity, this should go as Z square, sorry, as W square, because C has weight minus 1. And you can easily convince yourself that it's impossible for an analytic function to satisfy these results. Okay, as a function of Z, okay, if it goes as Z to the minus 4, okay, it has to have, I mean, it's incompatible with OPs of this kind. Okay, so it's not possible to find a function satisfying these properties. I mean, one simple proof of this is that you can take a contoured integral around W. Okay, because of this pole, you will get a non-zero answer. Okay, if you take Z, if you integrate Z around W. Okay, but now that contour can be deformed all the way to infinity, and at infinity, because it falls off as 1 over z to the 4, okay, it should vanish, the integral should vanish. So, not possible to find such a function. This implies that BZCW must be 0, and this in turn implies that as by taking the z goes to W limit, that this is 0. Okay, the inner product of the vacuum with itself is 0, because as z goes to W, you are supposed to pick up 1 over z minus W times the identity operator, right? And so that must vanish because this correlation for this 2-point function is 0. Is this clear? Pardon? Yeah, the point is there can be non-singular piece, but just by looking at the singular piece, you see that the correlation function must be 0, right? Think of now don't think of this as a OP, just think of this as a function of z and W, right? Or just as a function of z for a fixed W, right? And what we are saying is that this function is supposed to have a pole at z equal to W, and it should vanish as 1 over z to the 4 at large z, and those two are incompatible, right? Yeah, we are assuming that in the z plane there is also no other singularity because there is no other operator, right?
Or in other words, we know that P is 0, 2 and C 0 minus 1.
Yes.
And we know that any 2-point function.
That's another way of saying this. Yeah, yeah, that's true. But I'm now going to apply it for higher form function also. So imagine now you have B of Z, C of W1, C of W2. Okay. Now, as a function of Z, we have poles at W1 and W2. Okay, so for 3-point function, this argument doesn't work, right? Because there is no identity of this kind. So let's take this B of Z, C of W1, C of W2. So in the Z plane, has poles at W1 and W2, and it goes as z to the minus 4 for large z. Again, you can convince yourself that this is impossible, right? That there is no analytic function with this property. So we need, if we have a 1b, we need 4 c's. If you have 4 c's, right, then you can have a 1 over z minus w1, 1 over z minus w2, 1 over z minus w3, 1 over z minus w4. Okay. That is a function that falls over the 1 over z to the 4. Okay. So b of z so the function that can be non-zero is this one, b of z, c of w1, c of w2, c of w3, c of w4. This function as a function of z is allowed to have 4 separate poles, okay, and it should follow 1 over z to the 4 as z goes to infinity, and there is indeed such a function, okay, 1 over z minus w1, z minus w2, z minus w3, z minus w4 times some function of w1, w2, w3. This indeed has poles at 4 points, and it falls off as 1 over z to the 4. So this can be non-zero, and indeed this is non-zero. Is this clear? 4 also, yes. Okay, here, yeah, thank you. And then taking z goes to W4 limit, okay, we will pick up the residue, okay, and using that we can show that CW1, CW2, CW3 can be non-zero. Okay, I am not saying yet that it is non-zero, but it can be non-zero, okay, provided this is non-zero. Is this clear? Is this logic clear? Right. So if we just use C's, okay, you need 3 C's in order to get a non-zero answer, right? Because otherwise, if you insert a B and the C pair, okay, you will get into contradiction, right? Unless you have 3 C's to begin with.
And operator language means that you need C0, C1, C minus 1.
Yeah, that's right. In the operator language, that's what it means. Now, the reason that it's still not non-zero is because you have to worry about the anti-holomorphic side. So, similar analysis on the anti-holomorphic side implies that we need 3 C bars. Okay, that's why this is still, this has a problem, right? Because imagine that we take these 3 C's and insert a B bar C bar, B bar Z bar C bar W bar. Then again, as a function of Z bar, you have a problem, right? Because as a function of Z bar, you have a pole at Z bar equal to W bar, but it is supposed to fall off as 1 over Z bar to the 4 as Z bar goes to infinity. That again is a contradiction. So what is non-zero is this one. So C of Z1, C of Z2, C of Z3, C bar of W1 bar, C bar of W2 bar, C bar of W3 bar. This is non-zero, okay, and this is proportional to Z1 minus Z2, Z2 minus Z3, Z1 minus Z3. Okay, the proportionality constant you can choose by appropriately normalizing C. Right? Sometimes it's convenient to use 1 or minus 1, right? But that can be changed by redefining your C. Yeah, exactly, right? This is why here it's a can be non-zero, but it is actually non-zero, actually 0, unless also inside the C bar.
In general, we know what it was actually. From there, we could have computed without it.
Yes, you could.
Just see that all the others are 0 and
that's true, yeah. So there is a host number anomaly that you can use to also prove that the total number of C's, the total host number, host charge has to be 3 in order to get a non-zero answer. And that's what this is saying, right? The way I have defined host number, the host number has to be 3 in order to get a non-zero result in a sphere. B, C, 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 C is 0, right? If you have B, C, 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 C bar, C bar, C bar, that is non-zero. Okay, now then again some CFT result. So for holomorphic operator, now in some sense of course this is our choice how you define, but this is useful because with this expansion the n basically directly measures the L0 eigenvalue of the operator of this operator Fn. Okay, that is why we put this minus h over there. So you can also write Fn as integral okay. So this integral means this means this is contour around the origin and it includes 1 over 2 pi I factor. Okay, so that integral dz over z in this notation is just 1, okay, because 1 over 2 pi I is included in the definition of this contour integral. So the examples of such expansions T of z as ln okay, these coefficients just reflect the dimensions of this corresponding the weights of these corresponding operators, and there is a similar expansion for the anti-holomorphic fields. Now I give another CFT result. that if you want to calculate the commutator between this operator Fn and phi w bar, okay, phi is any operator, not necessarily even primary, okay, it's not holomorphic, then this is given by integral around w okay. This again follows from the fact that you are doing radial quantization, okay, and the standard property of the CFT. So what this contour means, that this is a contour integral around w. So the contour for z is winding around w. Okay. So this is determined, then is determined by the singular part of fz phi w bar op. Okay, non-singular parts will not contribute because you can string the contour around towards w, the z contour. No, all leading as well as all subleading, right? All singular contributions will contribute, singular parts will contribute, but the non-singular contributions will not contribute. Okay. And another point is that this commutator is replaced by anti-commutator if f and phi are Grassmann odd. Are there questions? Okay, so now I am going to introduce BRST current. Now here I am going to define this just as a CFT operator, okay. But the way it arises in the analysis of string worldsheet theory is via this Fadeev-Popov quantization. That once you understand how to do the Fadeev-Popov quantization starting from the original worldsheet theory, it automatically gives rise to a BRST operator, okay. And what I am going to describe here is that operator, okay. But for now, for our purpose, we will just think of this as some local operator defined in CFT with some nice properties. So here is the definition. JB is C times Tx. This is the energy momentum tensor for the x's plus B C del C, and JB bar is C bar T bar x plus B bar C bar del bar C bar. Okay. And both are Grassmann odd. And here, okay, again you see that you have product of B and C at the same point, right? So you have to do the subtraction, right? The way you define it is you have to look at define it as B of Z, C of CW del CW, look at the singular parts and subtract it off, right? That's the way you have to define this composite operators of this guy. Okay. And then we will define JB0 as integral JB of Z dz and JB bar of 0. Is this clear, the definition? So, exercise, if we try to calculate the anti-commutator, so both are Grassmann odd, JB is Grassmann odd, B is Grassmann odd. So, the anti-commutator you can calculate using this identity over here. So, this is given by integral around W JB of Z B of W dz. So, this we can now calculate by looking at the singular part of the JB with BOP, right. You see JB is given here, okay. So, the singular part is going to come from the OP of B with C and B with del C, okay. So, you work out the singular part, and here is the exercise to check that this is Tx of Z plus TBC of Z. Pardon? Sorry, W. Let me. Sorry, you had 0 component. No, see, this is here W is arbitrary coordinate, right. We are looking at 0 component is the fact that here you are doing the integral of JB of Z dz. Yeah, so JB0 is integral JBZ dz, right. That's what I am using here, JBZ dz. But B, so this should be a function of W, right, and that's what we are seeing here. It's a function of W, and that function is the total energy momentum tensor of X and BC. Okay. The X Tx is easy, right, because it's JB is there is a C times Tx and you know CBOP, right, that's 1 over Z minus W. So, that will give a simple pole. This is a little more complicated, right. This will, for example, have a double pole, right. So, one has to be a little more careful in doing this OP, right, but at the end you will find that this is given by the sum of these. Pardon? Two integrals? Okay. See, I am using this result over here, right. Fn was already an integral, right. Fn I erased. Fn was already an integral, yeah, right. And the idea is that when you take the commutator, that integral is now transferred to an integral around W. Okay, so basically the commutator is the difference between two integrals, one where the contour is just outside W, both integrals are around the origin, one where the commutator is just outside W, one where it's just inside W. So the difference is just a contour around W, right? That's the way the commutator works. Any other question on this? Similarly, there is a anti-holomorphic, right? Now, here is a harder exercise. Now there will be two integrals, right? Because here also now I am doing not JB of z but JB of 0, right? So there will be two integrals. So this is, you can write as integral over dw JB 0. I am just doing it in two steps with JB of w is around 0, right? All I have done here is that I have replaced JB 0 as integral over w around 0 of JB w, and now I am going to use this as integral over 0 dw. Now this commutator will become integral dz JB of z JB of w. Is this clear what we are doing? Right? The integral dw I kept separate, right? And then for this I use exactly the same kind of manipulation that I did here, right? Except that bw is replaced by JB of w. Okay. So you see that here the z integral is around w, and we have to look at the operator expansion, the singular parts in the JBZ JBW OP. And we have to look at the poles, single poles, right? If there is a 1 over z minus w to the 4, it does not matter, okay, because that will not contribute. Well, that will contribute. You have to expand, and the any function of z that multiplies it, you have to expand in parts of around z, in parts of z minus w, right? But at the end, you pick up the simple single pole terms, and the hard exercise is to show that this is 0. If d is 26. And similarly, for the anti-holomorphic part, so we define QB, the BRST charge, as JB 0 plus JB bar 0, and you have the relation that QB square is 0. Because JB and JB bar, of course, anti-commute, right? They have nothing to do with each other, right? So they anti-commute. So JB 0 square is 0 because of this relation, where this is 0, and JB bar 0 square is also 0 because of this relation. Is this clear? Okay. So with this, now we can define the physical states of the closed string. Okay, see here the total host number means left plus right, or holomorphic plus anti-holomorphic host number in the cohomology of QB. Okay, I'll explain what I mean by in the cohomology of QB. So, in the cohomology of QB means that for phi to be physical, you must have QB phi equal to 0. And we have to declare that phi is equivalent to phi plus QB lambda for any ghost number 1 state. Is this definition clear? So, we take states of ghost number 2, which means total ghost number, left plus right ghost number should be 2. It could be 0 2 or 2 0 or 1 1, right, or minus 1 3, it does not matter. Then in that sector you pick those states for which QB acting on the state is 0, and then we define an equivalence relation in that sector where phi and phi plus QB lambda are declared to be the same state, right. So, which means that if there is a state of the form QB lambda, right, that is automatically BRST invariant because QB square is 0, right. QB lambda acted on by QB gives you 0, okay, that is automatically BRST invariant, but we declare that as a 0 state, right, or sometimes it is called a null state. Okay, so you define an equivalence relation. Is this clear? Okay. I hope this is clear because this is not a correct definition, right? But to know the correct definition, you have to first appreciate this definition, right? But we will not correct it. Okay, this is almost true. This is true for most physical states. This definition is good enough, right? But there are some special cases for which this definition is not good enough, and you have to correct for those special cases. So, Bogdan, when should I stop? Okay, 10-15 minutes. Maybe I'll do it quickly. At least I should list the questions that we'll try to answer, and then we'll do that next time. So, correct definition. Okay, so as I said, this is almost correct, but this is not completely correct. So, let's cross this. So, correct definition. So, for this we first define B0 plus minus as B0 plus minus B0 bar, and L0 plus minus as L0 plus minus L0 bar. Then H is the subspace of states in CFT for which B0 minus on S equal to 0 and L0 minus on S equal to 0 for S belonging to H. Okay, so I define a subspace of states, okay, which are annotated by B0 minus and L0 minus. Okay, where B0 minus and L0 minus are defined this way. And now I define the physical states. Are states of ghost number 2 in H satisfying QB on phi equal to 0 and phi is equivalent to phi plus QB lambda, where both phi and lambda are in H. Okay. So, in other words, instead of working the full Hilbert space, okay, or full vector space of states, we work in a subspace of the vector space which is defined here. The importance of this is that only for this subspace of states, okay, we will be able to define amplitudes, scattering amplitudes of states. Okay, states outside this subspace, we cannot define scattering amplitudes. Okay, so that's why we restrict to subspaces of this kind. But as I said, for most practical applications, it doesn't really matter, right? Because you can always, even if you use this definition, right, you can find an element of the cohomology in that subspace. Okay, but in some special cases, it does matter, right? There are some physical states that appear here, but which cannot descend from this definition. Pardon? When I describe how to calculate scattering amplitudes, right, that definition will work only for the subspace of states, right, not for those. Right? Unless they belong to H, right, there is an ambiguity. I mean, you have to do some integral over the moduli space of Riemann surfaces, and the integrand will not be single valued function of the moduli space, right? So you cannot integrate it, right? So for in order that the integrand is a well defined single valued object in the moduli space, you have to restrict to this subspace. No, it doesn't follow. It's a definition at this stage, right? If you start from the original worldsheet formalism, right, then you can argue why it's equals number 2. Okay, but at this here I am only using the CFT language, right? I have not told you how the worldsheet translates to CFT, right? So that's why for in this approach we take this as a condition of the physical states. We need on the plane, right? For the correlation function to be non-zero, we need ghost number 3, 3, right? So which means that only 3-point correlation function will be non-zero, right? Once you have 4-point correlation function, you have ghost number 8, right? Because each carries ghost number 2. Okay? But we will see that the 4-point the way we want to the procedure for computing 4-point correlation function will automatically introduce some beats. Okay? So the ghost number always turns out to be 6. Okay, but that will come when I describe how to calculate amplitudes, right? Scattering amplitudes. Because scattering amplitudes are not just correlation functions of these vertex operators, it's the correlation functions of these vertex operators and something else integrated over the moduli space. Right? But that is the main goal of this lecture, to define what you have to compute to calculate the scattering amplitude. Which yeah, it's related to that, but I mean it's internally consistent. The procedure that I'll be describing is internally consistent, right? But as I said, the ghost number 2 you can also argue from the original worldsheet formulation by going through the gauge fixing procedure. So here is the result. This pen is running out of ink, so let me try this one. At is this visible or was black better? Is it okay? Where Vm is a dimension 1 matter primary. Example of such matter primaries are C bar, zeta mu nu, okay, this vortex operator, okay, under the condition that k square is 0 and k mu zeta mu nu is 0. Okay. This operator is a dimension 1 matter primary. Okay, once you satisfy these conditions, okay, and so this is a physical state. Okay. And indeed, you can see that this is a massless. This describe massless states because k square is 0. Okay. So this describes the graviton dilaton antisymmetric tensor, the two forms. So this describes graviton dilaton two form. So basically, the traceless symmetric part of zeta is the graviton, the trace part is the dilaton, and the antisymmetric part is a two form field. Okay, so this is the massless spectrum of bosonic string theory. And now let me just end by writing the main question that we will be addressing in these lectures. And that is how do we compute G loop n point S matrix of physical states for general G and N. So next time I'll describe the procedure for bosonic string, and then from the third lecture onwards I'll move on to fermionic strings. Okay, but this is the main question that we'll address, that you have to write an algorithm that tells you to calculate arbitrary loop, arbitrary endpoint S matrix of the physical state that we write here. Okay. And one of the key consistency relation, okay, is that if we take one of those external states, okay, and add a QB lambda, it should give the same answer, because there is an equivalence relation you have declared, right? The physical state and the state plus QB lambda is supposed to be the same state. So they better have the same S matrix. Okay, and we will also see what leads to that consistency relation. Okay, so this is the question that we will be trying to address. So I think I'll then stop today.